Good afternoon and welcome back. In this session, we have two talks. The first speaker is Nathaniel. He's a particle theorist at UCSB in Santa Barbara. His primary research interests are in particle phenomenology and the physics of beyond standard model. But he's also interested in the wider topics in cosmology, astroparticle, and quantum field theory, etc. Today, he'll talk about the quantum frontiers of particle physics.
Great. Thank you very much for the introduction, and thank you, of course, to the organizers for putting this all on. Good afternoon. Thank you, everyone, for being here. Out of curiosity, before I begin, is anyone in the audience a particle theorist or particle physicist? We have a few. Okay, very good. I'm delighted to see all of you, but I'm also actually delighted to see that most of the room is not, because as I understand it, my responsibility here, my opportunity with this talk today is to dive into quantum mechanics in its relation to particle physics, both the sense in which these two have been intertwined over the past century, but also the sense in which quantum mechanics really drives the open problems in particle physics. And many of the tools of quantum mechanics, the tools that are being developed today, including quantum sensing and quantum computation, really actually are, I think, going to give us the most promising methods of addressing the open problems of particle physics. So of course, this talk originally was imagined as a companion to David Gross's talk, which would have outlined the combination of special relativity and quantum mechanics into quantum field theory. I think we all miss David's presence a great deal, but I hope that I can at least do an adequate job in his stead. So of course, particle physics is in some sense the way that I like to think about it. It is just the natural consequence of the combination of special relativity and quantum mechanics into quantum field theory. We have certainly no time today to go over all the intricacies and miracles of quantum field theory, but when I talk about particle physics as a quantum mechanical phenomenon, I like to sort of leverage two heuristic facts. One of them, of course, comes from special relativity, which is that in any theory of local interactions, which you can describe with some space-time diagrams, like Feynman diagrams, if you have a process where two different types of particles can interact as a function of time, then, of course, special relativity in some sense tells you that you can turn this diagram on its side, and therefore there must also be processes by which you can take a particle and its antiparticle with enough energy, you can convert them into something entirely different. So special relativity in some sense tells us that particle physics is a form of alchemy, and we've leveraged this property over the last century, of course, to take the things that we know in the universe, collide them together at higher and higher energies to create the things that we did not previously know. But another crucial role, of course, is played by quantum mechanics itself, and this is encapsulated in some sense by the way in which quantum mechanics tells us that the vacuum is not the empty, uninteresting vacuum of classical physics, but instead is a rich and complicated environment of quantum fluctuations. And from the perspective of particle physics, that means that if there are degrees of freedom that are inaccessible to you, directly at your experiments, nonetheless, they leave their imprint in the form of quantum fluctuations. And we've basically, particle theorists, particle physicists have made use of these two observations over the last century to discover, of course, an increasingly large and complicated set of apparently fundamental particles, which we assemble together now in the form of the Standard Model. So, we like to show the Standard Model as these simple figures that have quarks up here, the charged and neutral leptons down here, the force carriers, the photon, the weak interactions, the strong interaction, and the Higgs at the center. But I want to emphasize, so this, of course, this is our current state of knowledge of fundamental physics at the shortest accessible distances, not including gravity. But I want to emphasize that this is not just a sort of list of particles and their properties, right? It's not simply an enumeration of the things that we find in nature. It is also a hypothesis about the underlying symmetries that combine and relate them. And probably we all here have a great deal of familiarity with the Higgs mechanism, since it has been very exciting physics of the last 15 years. But I just want to briefly give a heuristic of why the symmetries and the particle content of the Standard Model are so interestingly intertwined. So something interesting happens if you look at this particle content of the Standard Model, in particular if you look at the force carriers of electromagnetism and the weak interactions. You notice, the W and the Z, they're very heavy, but their masses are very different. And you notice the photon, of course, is massless. It's a long-range force carrier. And they all seem to have individually very different interactions. But if you make particular linear combinations of these degrees of freedom in the underlying theory, you notice that these peculiar linear combinations of those degrees of freedom have, in some sense, the same couplings to other particles in the Standard Model. And this is the first hint, right, that there is something deeper going on than just a set of disparate forces and particles in the universe, that in fact there is some sort of unification of electromagnetism in the weak interactions. And so, if you could just imagine the thought experiment for the time being, if you took a theorist and you said, I've made this observation that I have a unified structure of the interactions, can you go ahead, without telling them what the masses of all the standard model particles were, you say, can you go ahead and predict for me the mass spectrum of the standard model? And your theorist, he or she, would be very excited, and they would say, yes, symmetries like unified electroweak symmetry are very predictive, and given these particles and that underlying symmetry, I can give you a wonderful prediction. My prediction is that all of these particles will be exactly massless. And the reason for that is that the symmetry, the unification of the weak and electromagnetic interactions with the particles of the standard model is so constraining, of course, that you cannot give mass to any of them. Of course, then you make the same assignment to an experimentalist. The experimentalist goes out, measures the masses of all these particles, finds out, of course, they're not all the same. They're, in fact, dramatically different. And they, in fact, have a structure that exhibits very interesting patterns, but is wholly inconsistent with the unification of the interactions. So, in the standard model from the ground up, what we observed through the decades of discovering these new particles and interactions is a tension between the masses, the way in which they propagated through space, and their interactions with each other. And as we know, of course, these can be reconciled by a beautiful mechanism, which in particle physics we call the Higgs mechanism. Of course, it descends really from observations by Anderson. And the idea is that, of course, the underlying theory does, in fact, have this unified symmetry of the electroweak interactions. But there's also a degree of freedom, the Higgs, whose potential has a minimum which is away from the origin in its field space. And when it settles to the minimum energy configuration, it picks out a direction that breaks the underlying symmetry. So electroweak symmetry is a symmetry of the underlying theory, and therefore a symmetry of the interactions, but it is not necessarily a symmetry of the masses, because once the Higgs picks out some direction in its field space, breaks the electroweak symmetry, now degrees of freedom, other fields in the standard model as they propagate through space, the degree to which they interact with the Higgs determines their masses, which can be unequal. Right, so this reconciles this tension between this apparent unification of the interactions and the inequity of the masses. And so this, of course, has been a beautiful story. The idea that this could reconcile this tension was a beautiful theoretical idea that we had very maturely in the 1960s, but it took until 2012 to then proceed through a series of collider experiments to actually be able to produce evidence for the Higgs boson. And so that, of course, was triumphant physics that we were able to enjoy 13 years ago. And so with that, we've now completed the standard model. We have not just a list of all the particles that we've seen. That list of particles is now consistent with the bedrock principles of quantum mechanics. And this tension between the unity of the interactions and the disparities of the masses is reconciled by a mechanism that we've seen evidence for in nature. So you very often, talking to people about particle physics these days, especially from other parts of physics, they often ask a question which is in some sense reminiscent of something that we all remember Michelson saying at the end of the 19th century. So what did Michelson say? He said it in various forms in different lectures, but basically the conclusion was, prior to the advent of quantum mechanics and special relativity, this general feeling in the field that all of the major profound questions had been answered. And of course, that an eminent physicist has remarked that the future truths of physical science are to be looked for in the sixth place of decimals. And so you might be concerned that particle physics, having completed the standard model, that is what we're left to, which is going to measure things with increasing precision without hope of fundamentally new paradigms and principles. So the first message I just want to convey to you is that actually that is dramatically untrue. And it indeed is quantum mechanics combined with the theories of particle physics that we now have that tell us that the next century should be as exciting, if not more exciting, than the century of particle physics that's come before. You could come up with a long list of the problems and questions that particle physics is now facing. We only have time today to do any amount of justice to two of them, but just to briefly mention some of these problems to you. I've listed many of them here, but the thing that I want to emphasize about many of these problems is that many of them are intrinsically quantum mechanical in nature. Now, some of them are questions of like, how did the leopard get his spots? We have observed, for example, that there's 3 generations of fermions with interesting patterns of masses and mixings. That's an interesting question, but it doesn't necessarily have anything to do with quantum mechanics. But there are other problems, most notably the origin of mass, the nature of dark energy, and the apparent conservation of CP symmetry by the strong interactions. These are intrinsically quantum mechanical problems. The reason they're intrinsically quantum mechanical problems is they appear to be violations of what Murray Gell-Mann called the totalitarian principle. So the totalitarian principle, he said, was the idea that in physics, anything that is not forbidden is compulsory. And quantum mechanics makes the totalitarian principle real. A heuristic way you might say it is, of course, because quantum mechanics tells us that we explore all possible paths and outcomes, that anything that is not forbidden by the symmetries of the system will, of course, be explored in one way or the other. In the language of quantum field theory, it amounts to the statement that the renormalization group connects many different parameters that share the same symmetries or violate the same symmetries. And so it is very surprising if we see parameters that share or violate the same symmetries that have dramatically different sizes. And these questions of the origin of mass, the nature of dark energy, and the apparent conservation of CP by the strong interactions, these are all apparent violations by nature, as we see it, of the totalitarian principle. So quantum mechanics hasn't just given us, the content of the standard model, but now looking at the parameters of the standard model, quantum mechanics is what tells us that there must be more to this description than we currently know. Okay, but for the purposes of the rest of today's lecture, I just want to focus in on the top two questions, the origin of mass and the nature of dark matter. I want to describe these problems to you in some detail, their current state in the field of particle physics, the sense in which they may or may not be quantum mechanics problems. And then I want to finish the lecture just by pointing to or observing many of the ways in which things like quantum sensing and quantum computation are probably going to be our best chances for making progress on these questions. All right, so let's start with the origin of mass. So again, as we've said, right, the disparate masses of particles in the standard model are explained by the Higgs mechanism. Each particle obtains a mass from the Higgs vacuum expectation value proportional to the strength of its coupling. And you can compare this to the state of experimental data in a very convincing way. If you just plot the mass of the particles in the x-axis against an appropriate form of the coupling on the y-axis, you see indeed all of the heavy particles of the standard model fall upon the line which is predicted by the Higgs mechanism. And you'll notice the error bars to these predictions are the smallest for the heaviest particles of the standard model. Those are in some sense the easiest relations to test at colliders like the LHC. But right now, our knowledge of these relations extends down even to particles of what we'd call the second generation, for example, the coupling of the muon. So from this picture, you might say, right, the origin of mass is known. It is the Higgs mechanism of the standard model, and we see it verified by experiment. But there's actually a very heavy particle whose masses are comparable to the WZ in the top quark, which is not shown on this plot. Does anyone have a guess as to what particle that is? The Higgs, right. So you can ask, where does the Higgs fall in this plot? In other words, in some sense, in this parameterization, the coupling of the Higgs boson to itself should also obey the same relations as all of the other particles, and we should be able to make that same data point. And if you ask, given our current state of experimental knowledge, what our uncertainty is on the coupling of the Higgs to itself, it covers the entire plot. So in fact, we have no idea that the most important degree of freedom in this entire process, we have no idea, in fact, what its own coupling is. What does that mean in terms of our state of knowledge? Well, whenever we talk about the Higgs mechanism, we draw this nice wine bottle potential which characterizes the spontaneous breaking of electroweak symmetry. And in the context of the standard model, this comes from what we call a renormalizable potential. That just means there's a fixed number of terms consistent with the symmetry that control the potential for the Higgs. And so, in fact, in the standard model, given the measurement of the mass of the Higgs, we can also, therefore, predict its coupling to itself. But now you can take this beautiful theoretical prediction of the Higgs mechanism in the standard model, and you can ask what our current state of experimental knowledge is in terms of the shape of the potential. And it looks something like this. So what I'm doing here is if you could just imagine taking a slice from the origin out along this edge, you can make that slice right here. And then the shaded region is essentially showing you the envelope of possibilities of shapes of the Higgs potential consistent with our state of experimental knowledge. And the sorts of potentials that fit within this envelope include these very unusual looking shapes, which I'm sure are not realized in nature, but are completely consistent with everything that we know about the Higgs in the standard model. Okay. So what I want to emphasize to you is that although we've discovered a Higgs boson, which is consistent with the Higgs in the Standard Model, we actually have absolutely no idea if the way in which electroweak symmetry is broken is in the simplest way possible or is something more complex. Of course, this isn't just a question about the shapes of potentials. The actual shape of the Higgs potential has consequences for our understanding, although it sounds hyperbolic, of both the very beginning of the universe and its very end. So the sense in which it has relevance for the very beginning of the universe is, of course, we believe the universe, much like a good solid state material, started off at very high temperatures, in which at high temperatures electroweak symmetry was restored. As the universe cooled down, we expect that this high temperature effect gave way to the zero temperature Higgs potential, and that's when electroweak symmetry breaking happened. And of course, the question is then, is the breaking of electroweak symmetry a smooth crossover transition, or is there a first order electroweak phase transition? Now, in the Standard Model itself, once we've measured the mass of the Higgs boson, we have a sharp prediction that indeed the electroweak symmetry breaking phase transition in the early universe is a crossover. But any deviations in the potential of the Higgs due to new physics would change this conclusion and plausibly make it the case that the phase transition was first order in the early universe. So of course we have a very good idea of what that sort of phase transition means in, for example, boiling a pot of water. That sort of phase transition in the early universe is a very dramatic one. If the phase transition is first order, then of course what happens is a dramatically quantum mechanical effect in which the Higgs, at some point in space, the Higgs field tunnels from its minimum where electroweak symmetry was restored out to the vacuum where it's broken in the Standard Model. And because that tunneling happens at one point in space, then there's an expanding bubble of the new phase inside the old phase. And this happens at many points in the universe. Those bubbles expand and percolate until space-time is filled with the broken phase. But if this is indeed how electroweak symmetry was broken in the early universe, the collision of all of those bubbles has generated gravitational waves, which are susceptible to detection at gravitational wave observatories that we plan to build. So this question of, what exactly is the shape of the Higgs potential? Is it that given by the simplest Standard Model prediction, or is it something more complicated? Not only is it outside the reach of our current experimental knowledge, but getting clarity on its shape would then tell us a great deal, not just about how the universe began, but about experimental observables that we could hope to test in our lifetimes. It also tells us about the death of the universe. So another amazing thing, of course, that quantum mechanics tells us is that constants are not really constants. That is to say, in a relativistic theory of quantum mechanics, the constants of nature are in fact functions of the energy scale. And if you apply this logic to the potential of the Higgs boson, in particular the coupling of the Higgs to itself, and you ask what happens as you extrapolate it to higher and higher energies, something remarkable happens, which is that the coupling runs from positive values, which stabilizes the potential, to negative values. And the way you would interpret that in terms of the field space of the Higgs boson is the picture we've been discussing is true locally around the origin, but actually at large values in the field space of the Higgs boson, the potential runs over. And we actually don't know what happens after that. But we do know that, again, there would be quantum mechanical tunneling phenomenon that would take us from the vacuum that we currently occupy into one in which the Higgs vacuum expectation value was dramatically larger. Of course, if we were to tunnel out of our current vacuum into this other minimum, that would end the universe as we know it, and so that would be indeed some sense how our universe ends. Right now, of course, we don't have great knowledge of the value of the Higgs self-coupling, but measurement of the Higgs self-coupling, knowledge of that coupling, would tell us where in the space of possibilities we live, whether we are where we are in a range of metastability of our current vacuum, or whether the vacuum that we occupy is absolutely stable, or in fact whether it's sensitive to physics coming from quantum gravity to which we don't have direct experimental access. So where in this phase diagram we live, and the fate of the universe in some sense, is sensitive also to our knowledge of the Higgs self-coupling. There's not just a question of, in nature, is the shape of the Higgs potential the simple potential of the Standard Model or something more complicated. Even if it is just the shape that the Standard Model Higgs predicts, there's a much deeper question, which is what sets the scale itself. That is to say, it's the difference in field space between the origin and the minimum around which the Higgs gets a vacuum expectation value that sets the underlying scale of electroweak symmetry breaking, and therefore the mass scale for all the Standard Model particles. But of course, this is something that's incalculable in the Standard Model. It is simply a parameter that we would extract from data. in that sense, it's not like any of the other, it's not unlike any of the other 19 free parameters of the Standard Model. But it is importantly different in another way, which is that the scale of electroweak symmetry breaking is profoundly sensitive to short distance physics. So not only is it something that we cannot predict in the Standard Model, but in fact, its precise value depends in a radical way on physics that we have yet to access experimentally. Just to give some substance to those words, I want to develop an analogy from electromagnetism, which ties into one of the early stories of quantum mechanics. So of course, when you first, as an undergraduate or a high school student, learn about electromagnetism, you're confronted with the classical problem of the self-energy of an electron due to its own field, right? That the energy stored at the electric field of a charged particle diverges with the radius of that particle. And if you were to naively apply some relativistic thinking that this is a contribution to its self-energy, if you were looking at an electron at rest, you would say in that case, the observed rest mass of the electron is a sum of two contributions. It's a contribution from some bare piece, plus this contribution due to the energy stored in its own fields. And now you could ask yourself a question. Well, experimentally, we know that the radius of the electron is less than about 10 to the minus 18 centimeters. And so if you asked what's the amount of energy stored in its own electric field, the answer is it's greater than about 100 giga-electron volts. So at that point, you're presented with a puzzle. The puzzle is, why is the mass of the electron 511 kilo-electron volts, when that naively requires a cancellation between this 100 giga-electron volts and the bare piece to extremely fine precision. This seems somewhat absurd, but of course it could be true. But we know, just when we learn about the problem of the electron self-energy in our undergraduate electrodynamics course, we're told that something else actually happens. That in fact what happens is that there is a change of picture. That rather than classical electrodynamics being valid at all scales, there's a change of picture having to do with quantum mechanics that resolves this, and in fact tells us that the contributions to the rest mass of the electron are all of the same order as the observed quantity. Now, it's interesting to ask yourself how quantum mechanics comes into the rescue. In fact, there's a beautiful paper by Victor Weisskopf which explores this in some detail in the 1930s. And one of the first things that Weisskopf observed is he said, well, actually, naively, the first things that you might attempt to do by applying quantum mechanical reasoning to electromagnetism make the problem dramatically worse. In particular, if you think about an electron as having some finite radius, then you could consider the fluctuations of the electric field within the volume of the electron. And those fluctuations, of course, cause the electron to vibrate with some amplitude, and that vibration corresponds to some energy. And the energy of those fluctuations, in fact, scales not like 1 over the radius of the electron, but 1 over the square of the radius of the electron. So the problem actually, when you naively apply quantum mechanics to the problem, is considerably worse. Instead, of course, something rather beautiful happens. So in the late 1920s, Dirac tells us that, in fact, once we combine relativity and quantum mechanics, there is a new symmetry of the fundamental theory, which is the symmetries of CPT. And CPT, in fact, predicts the existence of a new particle, the positron, the antiparticle of the electron. But in some sense, the appearance of the positron, dictated by a symmetry, tells us that there is an important change of picture. Now, of course, you can compute the self-energy of the electron due not just to the fluctuations of the electron, but also the fluctuations of the positron. And what you see is this amounts to the vacuum of the theory changing on a length scale, which is dramatically longer than 10 to the minus 18 centimeters. So you can go ahead and do the calculation. These diagrams here are in what we would call old-fashioned perturbation theory. There's a contribution to the self-energy of the electron from its own field. And then there's a contribution where the electron is propagating, but actually there's a contribution from the self-energy of the positron. And when you add up these two contributions, what you see is something extraordinary happens. These two large contributions, which diverge as 1 over the radius of the electron, they cancel precisely. And the only thing that's left over is something that's actually proportional to the electron mass itself, with only a logarithmic sensitivity to physics at short distances. And so there's just a very interesting lesson here from taking this classical calculation of electron self-energy and applying the correct reasoning from quantum mechanics. The reasoning is basically, when you see that there appears to be some profound sensitivity to short distance physics, more often than not, what happens is a new symmetry appears and the picture changes in such a way as to remove that sensitivity to short distance physics. So that was true of the electron, and in fact, it was true of every other particle in the standard model that we discovered up until the discovery of the Higgs. But when we discovered the Higgs, we've in some sense gone back to where we were with our knowledge of the electron in classical electrodynamics. The Higgs boson has a self-energy due to its coupling the fields of all of the standard model particles that it couples to. And these precisely also give contributions to the rest mass of the Higgs, which are profoundly directly sensitive to physics at short distances. So we don't know how this story resolves itself. If we apply the same logic that worked for the electron, we should expect a change of picture associated with new symmetries and new particles. And very naively, that change of picture should happen around tera-electron-volt energies, which are around and somewhat above the energies we're currently probing at the LHC. Alternately, it's possible that there's no change of picture, but then we have this very interesting tension between the observed value of the Higgs mass parameter and its various microscopic contributions. So we don't know how this story plays out. I should say there's another origin of mass, right? I remember as an undergraduate, Frank Wilczek gave a Society of Physics students lecture to a group of us at Harvard. And he said, I'm going to teach you about the origin of mass. And I thought I was a precocious young undergraduate, and I raised my hand and said, well, you know, Professor Wilczek, isn't the origin of mass the Higgs mechanism? And he proceeded to tell me that no, in fact, the mass of most things had nothing to do with the violation of electroweak symmetry. That is to say, for example, if you ask what is the mass of a proton coming from, the mass of a proton as a composite object only has a very small contribution coming from the masses of the quarks that comprise it. That part is coming from electroweak symmetry breaking. In fact, the vast majority of it is just due to the energy density of the virtual excitations of quarks and electrons contained within the proton. Of course, this is true because of the miracle of the strong interactions. As David and Frank and Politzer discovered many years ago, the strong interactions start out very weak at high energies. Due to asymptotic freedom, they grow strong in the infrared, and they reach confinement and form bound states of strongly interacting particles. So of course, that takes us beyond the realm of perturbation theory and quantum field theory, and it limits our ability to actually compute what's going on. Some effects of strong interactions we can compute very well. For example, the contributions to the mass of the proton we can compute very well using Euclidean lattice quantum field theory, where we simply discretize the theory with imaginary time and are only limited by our computational resources. But there are many, many other phenomena associated with the strength of the strong interactions that are beyond our ability to compute with these conventional methods. An example that's very relevant to particle physicists, in fact, is the interpolation of physics between what happens when protons collide and the things that we actually observe in detectors. Right? So we've said, well, the standard model consists of all these different quarks, but we've never seen any of those quarks. What instead we've seen are patterns of radiation distributed in detectors with some very elaborate interpolation between our belief in the microscopic physics and what we actually observe. So for example, this is not even meant to be a cartoon. This is showing the collision of two protons together, the formation of various fundamental states with the strong interactions, but then the consequent physics that happens of the radiation of other gluons and other particles, and then the formation of hadrons, their propagation into space, and their interaction with detectors. We currently have no ability to describe this process from first principles. We can describe the quantum mechanics here with very good detail, and we can describe the physics here with very good detail. But in between, we actually have a number of essentially classical approximations. And so understanding the real-time dynamics of the strong interactions when we collide particles is something that lies beyond our present abilities. Briefly, I want to get to one other puzzle, which the puzzle isn't quantum mechanical in nature, but I'm going to bet you that the resolution will owe everything to quantum mechanics, and that is the nature of dark matter. So as we know, of course, most of the matter in the universe is not the stuff that we're made of. It is something for which we only have gravitational evidence. And the question on particle physicists' mind these days is, what is the underlying microscopic nature of the dark matter? And the problem is, there are altogether far too many possibilities for what it could be. So if you can see in the back of the room, this range of axes is going from ZeV scales to YeV scales. I don't even know that I remember all of the Greek prefixes for those quantities. But in this entire range, or equivalent here in electron volts, 10 to the minus 21 electron volts, which is when dark matter barely fits inside a galaxy, its wavelength is so large, to length scales that are at the scale of quantum gravity itself. And the problem is, as indicated by these various bars, we simply have far too many candidates for what dark matter could be across this vast range of scales. And so the experimental program of how we figure out what dark matter is seems at times impossible. So these are two of the very pressing questions that are facing particle physicists now, having to do with the origin of mass, both from the weak interactions and the strong interactions, and the nature of dark matter. And what I want to convey to you just in the last little bit of this talk is the very real sense in which the progress that we hope to make on these questions in the next century is going to be driven by quantum mechanics, and indeed many of the same quantum mechanical tools and methods that also animate the development of quantum computation and quantum sensing. So of course, one thing that we hope to do is to continue the long lineage of things that we've always done in particle physics, which is leverage the fact that we can smash together things we know to make things that we don't. Right now, we do that at the Large Hadron Collider, which is a 14 TeV proton-proton collider. But of course, most of the actual interactions that happen at the LHC aren't using 14 TeV energies. They're using about 1/10 of that. And that's, of course, because protons are composite objects, and you only get a fraction of their energy productively in collisions. So one thing you might imagine doing is the very naive thing, which is you build a bigger collider. And indeed, this is being considered. The next thing to do would be to build a proton-proton machine in a 100-kilometer ring, which would collide protons at 100 TeV. This is hard for many reasons. Among many other things, the amount of time it would take us to build and operate this collider is beyond all of our professional and, in fact, human lifetimes. But there is a possibility that is being very realistically pursued now in the US and in Europe, which I find very exciting and is also, in some sense, more quantum mechanical in nature. Which is instead of colliding things that we're made of, which is to instead collide a different ingredient in the standard model, something which is not stable. And the idea, in fact, is to collide muons and anti-muons. And what's so compelling about this is for various reasons, you can accelerate muons and anti-muons to collision energies that will be able to probe physics comparable to these 100 TeV proton-proton machines, but in rings that are the size of the existing Large Hadron Collider. Of course, this is a very complicated thing. It's going to require the development of technologies that we do not yet currently possess, but we believe we know how to do it. And one of the things that makes this so powerful as a technology for probing new physics is not just that it's colliding something that we've never collided before, but is actually using just some intrinsically quantum mechanical properties of high-energy muons. So of course, you might think if you accelerate muons and anti-muons to very high energies and smash them into each other, what you're going to get is only ever what happens when those two things come together. And indeed, a small fraction of the time, that's what happens. You annihilate the muon with the anti-muon, and you convert all of their energy into new physics. But really, a very high-energy muon actually is not just that classical particle. It is surrounded by a sort of a quantum cloud of virtual particles that it couples to, including the W and Z bosons and photons of the electroweak interactions. And so actually the most probable thing when you collide a muon and anti-muon together is not that they annihilate with each other, but rather that they radiate, that the virtual cloud of these electroweak bosons around them interacts, and those interactions in turn produce new physics. Now, this doesn't use all of the energy that's stored in the muon and the anti-muon, but it happens with a much higher probability. And so you can use this both to probe the properties of the Higgs boson to much greater precision, but also to have much better statistics in the search for new particles. So there's a sense really in which intrinsically quantum mechanical phenomenon could play a role in the next generation of collisions. And the power of this is such that, without getting too far into the details, please ask me at coffee or later on this week, the precision that you could get on the measurement of the Higgs potential takes us from this current state of uncertainty to, I think, considerable clarity as to the mechanism of electroweak symmetry breaking. It turns out the precision you could attain here is also good enough to know what the shape of the Higgs potential is, enough to say how the universe began and what its likely fate might be. And finally, apart from measuring the Higgs potential, just our ability to directly produce new particles in this environment will allow us, for example, to test the plausible explanations for what generates the scale of electroweak symmetry breaking. It's also true, remarkably, that if you collide muons together, because the collisions are primarily using the electroweak interactions, the most compelling candidates that we currently have for dark matter, which are ones where the dark matter is produced through its own weak interactions, all of those dark matter candidates can be also discovered or excluded at a muon collider. And so at least some of the most popular candidates for dark matter can also be directly probed at such a machine. Okay, so there's one path forward to some of the questions of particle physics, which goes in a conventional direction, colliding particles, but I would like to say, uses quantum mechanics in a way that we haven't really considered before in the context of high energy collisions. But there's also things that are really the tools of quantum information and computation that I think are entering particle physics in a new way and have the most interesting and compelling promise for the future. So one of them, of course, is quantum computation for the strong interactions. The problems that we currently have in the strong interactions, our inability to simulate real-time dynamics is, of course, precisely the thing that quantum computation can deliver. As we know, scattering in quantum field theory is a BQP process. And so indeed, ultimately, we should be able to resolve these questions of first principles scattering calculations at colliders using quantum computers in a way that we have absolutely no hope to do with classical computers. Now, obviously, the current state of play is far from that. Right now, there are very interesting, compelling simulations in 1+1 dimension that nonetheless isolate some of the relevant degrees of freedom in non-abelian gauge theories like the strong interactions and demonstrate good agreement with exact solutions in those dimensions. So there's a very long path from where we are to, of course, being able to, from first principles, calculate proton-proton collisions, but that path lies through quantum computation, and I see this as one of the very interesting and compelling use cases of quantum computers. Quantum sensing, I think, also has an incredible role to play. As I said, of course, possibly at a muon collider, we can probe these weakly interacting dark matter candidates, but the natural question you have is how we cover the rest of the space, especially dark matter candidates, for example, that are extremely light, 10 to the minus 21 electron volts, their wavelength barely fits inside a galaxy. It's impossible to imagine detecting those with any conventional particle physics technologies. But again, this is where quantum sensing and quantum precision comes into play. We're in an era where the whole suite of developments in foundational quantum mechanics, in AMO and condensed matter tabletop experiments really provide us the tools to make progress. So at the very lightest masses, for example, atomic clock frequency variations and cold atoms provide an amazing test of scalar dark matter. Precision measurement of nuclear spin precession gives us tests, for example, of axions. Various precision sensing methods allow us to detect other bosonic dark matter candidates via their absorption. And the space of things that is well beyond the scope of conventional particle physics experiments is really in the scope of quantum sensing. So I'm getting the time to wrap things up, but we've reached a good point. The takeaway I hope I've given you today, of course, is that particle physics over the last century, it really is the natural descendant of quantum mechanics and special relativity. That process has given us the standard model. But then there's two other things. If we look forward to the next century, there's two other things that quantum mechanics is doing for us. One is that it's framing some of the most pressing questions of particle physics, right? These questions that appear to be violations of what quantum mechanics leads us to expect. But then the other thing is that it's not just giving us questions without hope for answers. It's really the very same sort of computational and sensing developments that are being made for fields outside of particle physics that I think have the greatest promise of answering these problems of particle physics as well. So thanks very much. I'd be delighted, of course, to talk about any of this later on, but in the meantime, thank you for your time.
Thank you, Nathaniel, for this wonderful survey of this frontier of particle physics. We have a few minutes for questions. If you have a question, please raise your hand. One of our volunteers will bring a mic to you.
Thank you, that was very nice. So in this big figure for possible dark matter candidates with many orders of magnitude, don't know, is it conceivable that all of these dark matter particles exist, but with small abundances?
It absolutely is true, of course. I think we, in all fields of physics, like to operate by some form of Occam's razor in which the fewest, simplest, most minimal explanations seem to carry weight. But of course, the standard model is not the simplest or most minimal explanation for observed phenomena in stable matter. And so nature seems to have violated any dicta of simplicity there. It's absolutely true. One of the things that's very interesting, indeed, one of the opportunities about quantum sensing for ultralight dark matter that I find very compelling is not just the opportunities that it gives us if there's dark matter in the universe to use the existing dark matter abundance and measure it with quantum sensing. there are also opportunities that we have actually to use these methods to produce dark matter. You can always source dark matter in a laboratory if it couples to us, and then both source it and detect it. And again, quantum sensing provides avenues for some cases where that's possible. And so what's compelling about that is, if in this, I don't know if it's lucky or unlucky if our universe has all of these things with small abundances, but if that is the situation, we're not constrained to only be able to detect the small fraction, we can produce it. And that's one of the very compelling things I think that quantum technologies will enable.
Rajesh? Peter?
I mean, you didn't mention gravity in your.
Well, that's because Juan is coming. I would never dare to.
Yeah, but I'm not going in that direction. I just wanted your sense of whether you think some of the your sense of whether some of these explorations of dark matter in the context of extra dimensions and these things, what do you feel there, and it's even the experimental prospects?
Oh, good. Yeah. So I mean, obviously, one of the great. Indeed. So, of course, gravity has been left out of my entire story. We usually think about that because the apparent scale of gravity is so far separated from the other forces. But of course, one thing we've learned in the last 20, 25 years, and really originating in string theory, is that extra dimensions of varying sizes can bring the effective scales of these things much closer together. And if that is the case, then the methods of particle physics give us also a way of probing those underlying mechanisms. And so indeed, so a muon collider is particularly good for that. So of course, if we have extra dimensions where the Kaluza-Klein excitations are somewhere below 10 TeV, then those could be produced in abundance and understood very well. And in fact, the effective reach on Kaluza-Klein resonances of a muon collider goes to hundreds of TeV because of its sensitivity to indirect contributions, quantum mechanical effects. So those are all very compelling prospects. Something this is probably not the intention of your question, but there is something very interesting in the relation between quantum sensing for dark matter and gravitational waves, which is that basically all of the quantum sensing experiments that stand to give us sensitivity to dark matter across these ranges can also be used to look for stochastic gravitational waves of corresponding frequencies. Now, in many of those cases, you could ask, well, what is a motivated source for them? And that takes a little bit of thought. The standard astrophysical or standard model sources are not in those frequency ranges. But it is also an amazing coincidence that the same quantum sensing methods you would use to detect ultralight dark matter can also be turned to detecting stochastic gravitational wave signals, which brings these things together, in a very useful way. Yeah.
So what is the scale you're using to decide like where you go from wave-like to particle-like, because it's kind of right in the middle there. So what are you comparing with? Because
Good.
I would assume there are quite a few scales there, right? Because
so it's typically right. It's dictated by the occupancy. So given we know what the cosmological abundance of dark matter is, and then depending on the mass of the particle, if you're going to, that tells you what the density is, and now that you're going to ask, okay, how many modes do I have? And either it's starting to look like a classical field, or they're very high mass, smaller particle density, in which case they'd be better treated as particles. And so that's what really gives us this wave-like, particle-like dichotomy. Of course, it's not a perfect dichotomy.
Right, of course, yeah.
And indeed, many interesting quantum sensing methods, especially in MEV and EV energies, even though they're looking for what we call wave-like dark matter, of course, the signatures and the sensing is very much particle single deposition. Really, in some sense, so here the distinction is blurred. But yeah, it's the underlying answer is it's really what the occupancy is given the fixed dark matter energy density. The experimental signatures blend in this intermediate region, but are typically very particle-like on the far side.
So the experiments give a pretty good constraining value as to decide where it should be, this line.
Oh, well, I guess you would say more that given a certain system and a certain sensitivity to given energy, if there is dark matter there, the way that it interacts, it's really, this distinction is just to help us classify types of phenomenon, but if you can build experiments that are sensitive to energy depositions in this range, then you will be sensitive to the candidates that live here, and similarly here. And for example, a good example is dark matter detection that exists in this sort of electron volt energies that uses transition edge sensors. There are ways of exciting the system essentially with the wave nature of the dark matter, or individual excitations, and both of them can be picked up by TES-based experiments.
So Rajesh gave me the opportunity to ask this. I was not going to ask it. It's too philosophical for my taste. But since you talked about origin of mass, but the ultimate mystery is not mass. Ultimate mystery is space-time. I mean, quantum field theory, the field depends on space and time. Those are classical objects. But if we are to believe that quantum mechanics is the ultimate interpretation of the existence, then space-time must emerge quantum mechanically too. And as particle physicists, I'm sure you think about it. It's way above my pay grade. I don't think about these things.
No.
I do effective field theory and I take space-time as given. Okay.
Which is largely what I do as well. And of course, indeed, this question of the emergence of space and time is, again, a question for Juan later in this conference, which I'm sure he will address deftly. No, indeed, I think actually my personal position is very aligned with yours, which is that in the regimes to which I have any experimental access, effective field theory is the appropriate tool. And so I restrict my curiosity to the questions that effective field theory parameterizes. If it turns out, of course, that there are large extra dimensions and we have more access to quantum gravity at experimental scales, then of course I'm happy to be wrong.
But I was asking more a question of actual practice. So a large fraction of particle physics is not worrying about emergence of space-time?
That's right, because the length scale, yeah, indeed, the length scale in which that would occur is dramatically, naively given the Planck scale in 4 dimensions, the length scale is dramatically shorter, and it is essentially inconceivable to come up with experiments that meaningfully probe it. Not every particle physicist would agree with me, but that is the position I'm happy to take.
Well, I know Nathi Seibert certainly is thinking about it all the time. Whenever he says me, this is what he says. And a comment which will sound funny, but I don't mean it to be funny. Having worked on quantum computing for 26 years now, I hope your subject is not counting on quantum computing to solve your problem.
No, that's right.
But you'd be better off building a big accelerator because
it's opportunity. I guess, yeah, I suppose indeed, and I share your caution. It is not, of course, what I've chosen to work on, but I do think it is compelling that there are interesting questions in particle physics, for which the advantages of quantum computation are manifest. And of course, if we can get there, then that would be useful.
I know that there are more questions in the audience, but for the interest of time, we have to move on. So let's thank Nathaniel.
Thank you all very much.
Thank you.